All right, so in this section, I'm going to just prove a pretty quick little theorem about when a continuous function is injective, or otherwise known as one-to-one, right? That it must either be strictly increasing or strictly decreasing, which might sound surprising at first. I mean, just because it's sort of a strong thing to be able to say. But if you just think about it for a few seconds, like the mental image that forms in your mind, if a function is not strictly increasing or strictly decreasing, then there has to be some part, like some places where it's increasing and some places where it's decreasing, right? So if you have a place where it's increasing and then a place where it's decreasing, right, then then you end up hitting the same value multiple times, or similarly if it goes like this, um, you'll hit the same value multiple times, and that would violate the injectivity requirement. And this idea is actually just going to be, I mean, this is really the basis, or the sort of the core of the proof of this idea. So increasing and decreasing, not injective. Right. So let me just state the theorem here. So this is theorem 18.6. Let f be a continuous function on an interval I with f1 to 1. Then either f is strictly increasing or f is strictly decreasing. Okay. So here is the proof. So first, well, here, let me just start writing up here to make sure I have enough room. So first, we show that so if a less than b less than c in I, then f of b is between f of a and f of c. And remember, when we say that, we're wording it this way because we don't know whether f is actually increasing or decreasing. So we don't know whether the string of inequality should go one way or another. But either way, f of b is going to be in between them, whatever order they might be in. So if b is basically, it's like if b is between a and c in the domain, then f of b is between f of a and f of c. And this is what will ultimately, like, I mean, this ends up being equivalent to either f being increasing or f being decreasing everywhere, and you'll see why. But so let's prove this. So to see this, suppose, without loss of generality, that f of b is greater than the maximum of f of a and f of c. So if f, basically, we're going to do this kind of by contraposition or contradiction, right? So we're going to assume that f of b is not between these two values. So for one thing, we don't actually know which of these two values is bigger, but it doesn't end up mattering for the argument. But we also don't know, when we say it's not between them, that means that it could be like bigger than both of them, or it could be smaller than both of them. But the argument for both of those cases is basically the same thing. I mean, it's just with some inequalities flipped around. So we're going to assume that f of b is bigger than both of them, and leave the other mirrored argument out just for expedience. So okay, then since f of b is greater than f of a, the intermediate value theorem, well, oh, first, okay, sorry, hold on. Then pick y such that f of b is greater than y, greater than the maximum of f of a and f of c. Then since f of b greater than y greater than f of a, the intermediate value theorem tells us that there exists, let's say, x1 in AB such that f of x1 equals y. Similarly, there exists an x2 in BC such that f of x2 equals y. This means f of x1 equals f of x2, but x1 is not equal to x2, violating injectivity. Right, so if you go back, so basically it's like, we have this picture here, and we picked our y here, and we found, two, so x1, x2, two values, or two x values where f achieved the value y, right? So this is like f of a, f of b, f of c. It literally is exactly this picture, right? Except we don't know which of these two endpoints is higher, but it doesn't matter. Okay, so that's the first part done, right? I mean, that's just straight from the intermediate value theorem. So now we know that f of b is always between f of a and f of c when a less than b less than c. So now we want to show f is strictly increasing or decreasing. The problem is, like, it's hard to, from this directly show that it's either strictly increasing or strictly decreasing, because we just don't know which of the two things it is, right? We haven't gotten any information about that. So the question is, how do we tell, like, how to tell which, right? Choose a naught less than b naught, right? How to tell whether f is strictly increasing or strictly decreasing? The natural thing to do is just test it, right? Just look at two values of f and see which one's bigger. And that'll tell you if it's supposed to be, if we expect it to be strictly increasing or strictly decreasing. Of course, then we have to actually prove that it is that thing, but we can just sort of test it with two values first to figure out which direction we're trying to go, right? So choose a naught less than b naught in I arbitrarily, and suppose, again without loss of generality, that f of a naught is less than f of b naught. Then we want to show that f is increasing, strictly, of course, right? So if we test at two values and find that this one's bigger than this one, that means f should be increasing. So we want to actually show that now. Of course, again, there's another case where f of a naught is greater than f of b naught, but the proof is like identical with some inequalities flipped around. So I'm going to just skip that. So basically, so from this point, we know that right. Okay, so there's just a bunch of inequalities. So we know that f of x is less than f of a naught for x less than a naught because we know that f of a naught must be between, between f of x and f of b naught. And of course, we know that f of b naught is bigger than f of a naught. So that means f of x has to be less than f of a naught, right? So then also f of a naught is less than f of x, less than f of b naught for a naught less than x less than b naught, because f of x must be between f of a naught and f of b naught, right? This is all just by this thing we just proved up here, right? That when one x value is in between two others, then the f, the value of f at that point is in between the other two values of f. And then also, similarly, f of b naught is less than f of x for b naught less than x, because, f of b naught must be between f of a naught and f of x, okay? So basically we're just, building up these inequalities, and now let's and then they say, so in particular, well, yeah, f of x less than f of a naught for all x less than a naught. We literally, that's the first one we listed off over here. And then also f of a naught is less than f of x for x greater than a naught, because actually between these two cases, right, that's always true. Either x is between them, and then f of x is bigger than f of a naught, or x is bigger than b naught, in which case f of x is bigger than f of b naught, which in turn is bigger than f of a naught. So whenever x is bigger than f of a, or whenever x is bigger than a naught, f of x is bigger than f of a naught. Okay, so and f of a naught is less than f of x for all x greater than a naught. Okay. Okay, so now let x1, x2 be an I with x1 less than x2. We want to show that f of x1 is less than f of x2. Okay, so I'm going to just kind of draw a picture here. So I don't know. There are like three cases, I guess. So let's see. It's the same logic as before. Okay, so the first case is that a naught is over here, and then x1 and x2 are like this. So then f of x1 is less than f of x2 less than f of a naught, or less than or equal to at least, because f of x2 is between f of x1 and f of a naught, right? Because x2 is between x1 and a naught. I mean, let's just assume that, like, I think they let these inequalities be, oh yeah. So actually in this case, they consider this to be strict, right? Okay, so this is, again, just by what we proved before. So since x2 is between x1 and a naught, then f of x2 has to be between f of x1 and f of a naught. But we know that f of x1 is less than f of a naught, so f of x2 has to be bigger than f of x1, right? Then similarly, you could have like a naught and then like x1. This is less than or equal to, and this is also less than or equal to x2, in which case we just know that f of x1 is less than or equal to f of a naught, less than or equal to f of x2, just by what we showed up here, right? And that, of course, the inequality between, so f of x1 is less than f of x2 because they're not equal, right? Since x1 is not equal to x2, right? They have different values, and we already knew that, and so this tells us that f of x1 is less than or equal to f of x2, but we know that they're not equal. So that means that this one is less than this one. And then the last case is, we have a naught, and then x1, and then x2, and this is strict inequality. And then this is the same as so this is similar to the first case. Right, basically x1 is in between a naught and x2. That means that f of x1 is in between f of a naught and f of x2. And we know that f of x2 is bigger than f of a naught. So that means that f of x1 has to be smaller than f of x2. Okay? All right, so that concludes this lecture. Thank you for watching, and see you in the next one.